All right, welcome back everyone. Today we are going to wrap up the third part of the torque chapter, which is going to focus on mostly rolling without slipping, but we're also going to talk about kinetic energy and how to apply conservation of energy to rolling without slipping. And that is kind of going to close up the torque chapter. And at this point we should have covered everything that's going to be on the exam, and we're just going to see that there are not many new equations we have to deal with today. We mostly have to define a new type of motion and a new type of kinetic energy, but other than that, that's kind of it. All right, so we're going to spend a little bit of time doing that, just to recap that part, and then we're going to apply it to a problem where we're going to revisit torque net equals I alpha because it's important, particularly in the context of rolling without slipping. And we're going to apply conservation of mechanical energy to an object that is rolling without slipping. So, we'll start with kinetic energy. Let's do that. So, kinetic energy is not something new. We've already talked about kinetic energy in the work on energy chapter. And we just called it kinetic energy because it was the only one we had, but we're probably going to call it linear or translational kinetic energy. So if I have a block that has a mass m and a speed v, then the linear slash translational kinetic energy is going to be given by k, call it sub t for translational, is 1/2 mv squared. Okay, nothing new there. We've known this forever, or ever since we've defined kinetic energy anyway, and that's because we only had one type of motion, which is translational motion. Like the block has a specific shape, and every point of the block that you can imagine moves to the right with speed v. So that's translation. It's translational motion. It's the whole block translates from left to right. Okay. New type of motion that we encountered in this chapter is rotational motion, right? So you can think of that as a cylinder spinning. I mean, it could be a drill bit, it could be whatever you want. But let's say that we have rotational motion. We have a spinning cylinder, right? And it has a moment of inertia I with respect to its center of mass, so I center of mass. And omega is the angular speed at which it rotates, okay? Well, this is a different type of motion, right? This is rotational motion, and it's very separate from linear motion. Here, all the points of the cylinder spin about the center of mass. So this is rotational motion, which means that we're going to define rotational kinetic energy, and that is going to be K R is going to be equal to 1/2 I center of mass omega squared. So if I have something that is just undergoing pure rotation, again, a rotating drill bit, for example, then its kinetic energy is 1/2 I omega squared. Whereas if I have something that is sliding, like maybe a bar of soap on a slippery floor, that would be linear motion, and it's going to be linear kinetic energy 1/2 mv squared. And these two types of motion have nothing to do with one another. Right? The bar of soap is very different from the rotating drill bit. Now, it turns out that in a specific case called rolling without slipping, we combine both of these motions for something, let's say, like a bicycle wheel or a bowling ball, or something that, as it moves in one direction, seemingly linearly, it also rotates, and that's how it gets there. And so if that's the case, then I have both types of motion, therefore I have both types of kinetic energy that I have to account for. So that's the main point for today, is to talk about rolling without slipping. All right. And this is the superposition of linear motion and rotational motion for which the contact point never slips. Well, this is going to make more sense in a second. Okay, so let's take the bowling ball or the bicycle wheel, whatever example makes more sense to you. Okay. If I look at it and I say, this is a ball that is going to eventually roll without slipping on the ground, but I just look at it as is, and I say that I would like the ball to have a motion that is translational motion, right? In other words, I could take the ball and I would make sure that it doesn't rotate at all. I just take it and I'd slide it to the right as a whole, right? And so the center of mass would have a speed v then, but in fact every point of the ball, the top, the bottom, the middle, any point you can imagine would have the same speed v, because that is what translational motion is. The entire object moves in a single direction with the same speed for every point of that object, okay? So that's linear motion or translational motion. However, I could also take this ball, right, and I could rotate it, I could spin it, right? Maybe like a basketball on my finger. I'd probably not do that with a bowling ball, but you get the idea, is that it doesn't have to go left or right. It doesn't have to go up or down. It could just spin around in place, right? And maybe just to make things easy to see, I look at it from above as it spins. And maybe it spins, let's say clockwise, just to pick one. And this is going to be omega, right? The angular speed at which it rotates. Well, as it rotates, the speed of the center of mass is 0 because it doesn't move left or right. You just have rotation about the center of mass. However, we saw last week that the speed of this point here is going to be v is equal to r omega. And the speed of this point here is going to be also the same, just in the other direction. This is going to be v is equal to r omega. Okay, so on the left I have translational motion, and in the middle here I have rotational motion. Okay, so by the way, k for translational motion is going to be 1/2 m v center of mass squared, and then k rotational motion is going to be 1/2 I center of mass omega squared. Okay, so it has a moment of inertia, I center of mass, let's call it. Now, rolling without slipping is the superposition of the two, meaning that if I combine the two, right, if I actually put one on top of the other is really what superposition means. What am I going to get? Well, I need to get motion in which the contact point with the ground, if now the bowling ball is not just being moved left to right without rotating or just spinning without moving, it is now rolling on the floor, which causes it to move, then I need my contact point here to have no speed relative to the ground, because I do not allow the contact point to slip. That is what rolling without slipping means, right? So when you lock your brakes on your bike and you skid on the icy road, that is not rolling without slipping, of course. Rolling without slipping is you pedal, the tire grips the road, and you move forward. And in fact, if the tire completes one full revolution, you move forward one circumference, right? Because it never slips on the road. And so the combination of the two, if I need V to be 0 here because I have a no-slip condition between the contact point, at the contact point between the ball and the ground, then I need this to cancel this, right? So in other words, it has to be the case that here V is R omega, which means that all of these guys are R omega. If that's true, then this cancels this and I get the no-slip condition. Okay. But then I have to consider all the other points. Then V center of mass plus, well, 0, because V center of mass is 0 here, becomes R omega. This is a fundamental property of rolling without slipping, which is that V center of mass is R omega. The faster the ball spins, the faster it moves forward. The faster the bike tire spins, the faster you move forward. Okay? And then at the top here, something interesting is that you get double the speed. You get 2, well, call it V top. 2R omega. Now the reason for that is that what's really happening here is that at any moment the entire ball is pivoting over the contact point with the ground. Okay, so it's really doing this. It's the whole thing is swinging over the contact point with the ground. But it's really hard to see because as it does that, then the next contact point hits the ground, then the next contact point hits the ground, then the next contact point hits the ground. So you never really see that it's the entire top of the ball that's swinging over the contact point. You just kind of see the ball moving to the right as it rotates like that. So you see the combination of these two things, but it's very hard to see that it actually is at any given moment rotating about the contact point with the ground. But that's why the top moves twice as fast as the middle, because it's twice as far from the contact point. So this is rolling without slipping. Okay, well, what it means, of course, is that the kinetic energy for rolling without slipping is going to be the sum of the two. I have both linear motion of my center of mass. I have 1/2 mv center of mass squared plus 1/2 I center of mass omega squared. I have both linear motion of my center of mass. That is because as it moves, let's say this, as the ball rolls without slipping, the center of mass moves to the right in a straight line. That is linear motion. But at the same time, I do have rotational motion about the center of mass. Right? The combination of these two gives me this overall, which is rolling without slipping. So when dealing with rolling without slipping, if you're going to write energy, in particular kinetic energy, you have to account for both the linear kinetic energy or the translational kinetic energy and the rotational kinetic energy. So that's the key to keep in mind here when it comes to rolling without slipping. Now, I will say, just to emphasize this a little bit more, that V center of mass is R omega is a property of rolling without slipping. The faster the bike wheel spins, the faster you move forward, but it also translates to acceleration. Okay, so rolling without slipping means the following. It means that V center of mass is equal to R omega, and therefore A center of mass is R alpha. Very important to keep that in mind. All right. So that is rolling without slipping. And that is the main point that I wanted to touch on today. We're going to do a problem where we're going to first use torque net equals I alpha and kind of revisit stuff from last week, and then we're going to apply conservation of energy. Okay, so the problem in question is the following. We have a solid sphere, and we have the moment of inertia about its center of mass that's given, that is at rest at the top of an incline, and its center of mass is a height h above the ground. And we have an angle theta at the base of the incline, and coefficient of static friction mu s between the sphere and the incline. Now it turns out we need static friction so that the contact point does not slip. So that's a bit of a weird one where the only way you get rolling without slipping is if you get static friction that is sufficient to keep the contact point from slipping down the incline. Now we'll see what that does in terms of forces, but the point is the sphere is released from rest, it rolls down without slipping. The first question is find the acceleration of the center of mass of the sphere, a center of mass basically, as it rolls down the incline. Now I'm going to do it with two different methods. Well, the same method with two different pivot points, let's call it that. Because I want to fully review what we did last week and add to it the things that we need for rolling without slipping. Okay, so here's the sphere as it rolls down this incline. Okay. And I'm going to draw the forces acting on it. Now the weight force is going to be applied at the center of mass. So that's going to be mg. The normal force originates at the contact point and goes through the center of mass. It's going to be N. And then we said that the property of rolling without slipping is that the contact point with the incline does not slip. Now, it wants to slip, and if it were to slip, it would slip down the incline, but the reason it does not is because static friction prevents it from slipping down the incline. And of course, it's because of static friction that you get the rolling without slipping, because at any moment here, the entire top of the sphere is going to try to rotate, or is going to rotate rather, about the contact point. Okay. Quick reminder from before where we were dealing with inclines, right? Let me do this. This angle here is theta, right? Same as the case of a block on an incline. The angle between the perpendicular to the surface and the weight force is theta if the base angle is theta on the incline. And so we're going to apply the equations required to find the acceleration of the center of mass, right? But of course there's two types of motion going on because it is rolling without slipping. Rolling without slipping is the combination of linear motion of the center of mass and rotational motion about the center of mass. It's a combination of the two. And so with that in mind, what we're going to say is that if I have linear motion and rotational motion, well, I need F net equals ma for the linear motion, and I need torque net equals I alpha for the rotational motion. And again, these equations do not know about each other. They describe different types of motion, right? So they each live in their own little world. But we're going to tie them all together because we have a cylinder, or I'm sorry, a sphere that is rolling without slipping in this case. Okay, so let's first agree that acceleration of the center of mass is going to be in this direction, and that alpha, the angular acceleration, is going to be in this direction. Okay, if we agree on that, then we can do the following. We can make this x, this y, and this clockwise direction, the positive direction for rotation. Okay, just to make things easier. Now, let's deal with the linear motion first. Okay, linear motion, what we're going to have is F net x is m, a center of mass, that's the acceleration in the x direction, F net y, which is perpendicular to the incline, is going to be 0 because no motion along y. Okay, this is not new. We've done this many times before. Okay, so then let's write f net x and f net y. Okay, f net x, hopefully everybody agrees at this point that it's going to be the x component of weight, which is mg sine theta, minus static friction is equal to ma center of mass. And in the y direction, I get n minus mg cosine of theta is equal to 0, which is not going to be very useful, it turns out, because I don't need the normal force. And the reason is I have no reason to say that Fs is mu Sn, because nothing about this problem suggests that I'm on the verge of slipping, right? In the previous problems that we did with static friction, yeah, it was always phrased in such a way as to indicate, oh, what is the max force I can pull with before the block slips, right? This is saying you're on the verge of slipping. Tell me what that looks like. There's nothing about that here. Static friction is static friction. Probably is less than mu Sn anyway. But what we shouldn't do is assume that it is mu Sn. So we'll leave it as is, and we don't need the normal force. But that's okay. Let's just write our equations. Then let's deal with rotational motion. Okay, now rotational motion is torque net equals I alpha. Now, as a quick reminder, I have I center of mass is equal to, this is a solid sphere, so it's 2/5 of big M r squared. Okay, so I'm going to put that over here just as a reminder. All right, then rotational motion is going to be torque net is equal to I alpha. Now I know that to write torque net equals I alpha, I have to choose a pivot, and I have to compute the net torque and the moment of inertia about that pivot. Okay, well, I'm going to therefore choose the center of mass as my pivot because I already have the moment of inertia about the center of mass. So let me make this my pivot here, okay? And like I said earlier, I'm going to do this for now, then later I'm going to change the pivot and I'm going to make it the contact point, and we'll see what happens then. But for now, this is my pivot. Okay, so torque net is equal to I alpha. Any force that goes through the pivot creates no torque about that pivot. So the normal force creates no torque about the pivot. The weight force creates no torque about the pivot. The only force that creates a torque about the pivot is static friction. It is the reason why we get rotation clockwise like this. This is a 90-degree angle, and torque of Fs is going to be positive. The distance between the pivot and the force is r. The force is Fs. Sine of 90, which is the angle between r and Fs. And all the other forces create no torque about my pivot. Okay. So actually, let me do this. This is a bit of planning ahead. Let me just okay. So those are the different torques, which means that torque net is equal to I alpha. If I choose my pivot to be the center of mass, I'm going to get I center of mass here, and simply it's going to be RFS, sine of 90 is 1, is equal to 2/5 m r squared alpha. Okay. This will simplify, by the way. I can get rid of the r like this. Okay, so I get Fs is 2mr alpha, which, by the way, tells me what Fs is, right? So it's not mu Sn, it's 2/5 mr alpha. Okay, so let's see if we can fit all of this in one page. There we go, one screen. So what's important here? We have two types of motion because it's rolling without slipping. We write our equations for linear motion, write our equation for rotational motion. However, these equations do not know about each other, right? They describe different types of motion, and there's no connection between the two, but I know there has to be because I'm rolling without slipping. And I keep saying, the faster the bike wheel spins, the faster I have to move forward. Therefore, there has to be a connection between the two types of motion, which there is, and that is rolling without slipping allows you to write the following. It allows you to say that V center of mass is R omega, which right now is not helpful because I'm not dealing with speeds, I'm dealing with accelerations, but it's going to be helpful in the next question when we do conservation of energy. But that's okay because I also get A center of mass is R alpha. Okay, so this connects this to this, and I want to find A center of mass. So I'm going to say A center of mass is R alpha. All right. So let me make a copy of our equations here. We're going to bring them down here, and we are going to, so we have Fs is 2/5 mr squared, and we're going to solve this for A center of mass. Okay, and then A center of mass is R alpha. Okay, that's everything we just derived. Okay, well, I know what Fs is. And by the way, because R alpha is A center of mass, I'm going to say that Fs is 2/5 of m A center of mass. At which point, I can plug Fs into the first equation. That's going to give me mg sine theta minus Fs, which is minus 2/5 of m A center of mass is equal to ma center of mass. Okay, so then mg sine theta is equal to, well, 2/5 plus 1 is actually 7/5 of m A center of mass. Cancel the m's, and I get A center of mass is 5/7 g sine theta. Okay, but I had to write equations for both linear motion and rotational motion, plus rolling without slipping to connect them all together. All right? But not that bad. I mean, just a nice summary of everything we've learned so far. With this is the new stuff from today, right? The rolling without slipping condition. Now, I said that I was going to solve this with two different pivot points, and so we did the center of mass as our pivot point. Now let's take all of this, make a copy, and go solve it with a different pivot point. Now, what's going to be interesting is to see what changes versus what doesn't. Okay, so here we're going to have the same setup as before with a different pivot. Okay, so let me just fix that off the bat. We don't want that to be our pivot. I'm going to choose the contact point with the incline to be the pivot. So my pivot is going to be right here. Okay, so the pivot is no longer the center of mass, so this changes. It's going to be the contact point. Okay, so that's different. What else changes? Okay, well, linear motion never cared about pivots. We never talked about pivots before we did the torque chapter. So none of this changes. Rolling without slipping is rolling without slipping. None of this changes. But I need my torque to be computed with respect to my pivot and my moment of inertia to be computed with respect to my pivot. So now this does change here. I center of mass becomes I contact times alpha, and this equation is going to change because torque net is going to change. Okay, so let's evaluate torque net now. Okay, Torque from the normal. Any force that goes through the contact point does not create a torque about that contact point. Normal force goes straight through, creates no torque about that point. So does the static friction force, creates no torque about that point. However, mg does not go through the contact point, and therefore, relative to my pivot, creates a torque. If I only look at mg, it tends to want to rotate this thing like this, and so it's going to be positive torque. The distance between my pivot and mg is the radius of the sphere times the force mg times the angle between r and mg, that's theta. So my net torque is going to be rmg sine theta. My moment of inertia is eye contact, which is not this, which means I have to use the parallel axis theorem to find eye contact. Okay, so that's, again, parallel axis theorem, nothing difficult about it except you have to realize that you have to apply it. Okay, so let's go do that. Let's use the parallel axis theorem because we need that to get the right moment of inertia. Okay, so what do we have? We have a sphere that has a center of mass right here, but we have a pivot that's right here, and we want to rotate about that pivot, not about the center of mass, right? So we need to know the distance between the two, which is r, and we can say that eye contact is eye center of mass plus, well, if the sphere has a mass m and there's a distance d between the two axes, between here and here, well, the answer is plus md squared. So here's going to be plus mr squared. That's the added difficulty from choosing a pivot that's at the contact point and not at the center of mass. It is that much harder to rotate the sphere about that point. Okay, so I center of mass, well, that's 2/5 mr squared plus mr squared. That's going to be 7/5 of mr squared. And if you're paying attention, this already looks familiar. Okay. So what equations do I have? I have these equations that, I had earlier. They have not changed. I also have a center of mass is r alpha. That is just because of rolling without slipping. That has not changed. And then I have torque net is equal to I alpha. Torque net is rmg sine theta, and I is this. Okay, so I'm going to have r mg sine theta, that is my net torque, is equal to moment of inertia 7/5 of mr squared times alpha. Okay, which I can simplify a smidge because r here cancels the square. And because r alpha is a center of mass, I get 7/5 m a center of mass. Which is nice because now I can just conclude directly from the last equation that a center of mass is equal to, after simplifying m, 5/7 of g sine theta. And there we go. So, same thing, of course. It's the same acceleration I found earlier, just if you're not sure. I just did it with a different pivot point. And this goes back to what we said the very first session we started torque. We said the pivot point can be mathematically anything. You just have to be consistent, right? Pick your pivot, compute your torque net about the pivot. If you need moment of inertia, compute your moment of inertia about the pivot. And it doesn't matter whether it's the center of mass or the contact point. At the end, it all comes together nicely. Now, if we do it with the center of mass, which offers the upside of not having to use the parallel axis theorem, because I already know I center of mass, it's given, Well, then we do have to do a little bit more work down here of combining equations together to get a center of mass, which, I mean, fair enough. That would still be my preference. But it's not that much harder. It's kind of a wash right here because, like, look, yeah, I don't get to use I center of mass directly. I have to use the parallel axis theorem. But, you know, I just get the answer right away with the last equation. I don't have to combine anything. I just get an equation that gives me a center of mass like that. So not too bad, pretty nice. In both cases, we did the same thing, just with a different pivot point, which is something, you know, I find is worth seeing at least once. And as an added bonus, it allowed us to review the parallel axis theorem again. We talked about that last time. Okay, so then with all of this said, we can move on to question 2, which tells us that this thing rolls without slipping down the incline from rest and has an initial height relative to the ground of its center of mass, that is h. Okay, so h is from the ground to the center of mass, just to be clear. Starts at rest, rolls without slipping down the incline, and we want to figure out how fast the center of mass is moving at the bottom of the incline. Okay, so that would be v center of mass down here. Okay, given that up here, v is equal to 0, omega is equal to 0, right? By the way, down here, we also have omega, right? Call it omega final if you want, because it's rolling without slipping. Okay. So I will choose the ground to be my reference for gravitational potential energy, which is pretty common, and I'm going to apply conservation of energy, which most of the time seems weird because you're like, hold on. Don't we have friction? Because without friction, we cannot have rolling without slipping. It's like, well, that's true. Static friction that we have, though, because it's rolling without slipping. And static friction is very different from kinetic friction. Now, if you have a block sliding down an incline with kinetic friction, the friction between the two as the block slides creates heat. That heat is energy, but it's lost. Okay, it's lost forever. The block does not know how to take heat and convert it back into kinetic energy. Right? It's not a steam engine, it's just a block. So yes, if there is kinetic friction and you have a block sliding down an incline, conservation of energy is out. You may not use it. However, if you have a sphere or a cylinder or an object that can roll without slipping down the incline, then it is not kinetic friction that's involved, it's static friction. And that is very different because static friction does not cause any energy to be lost. There's actually no rubbing of the two surfaces creating heat. Okay? And so what happens is that static friction is in fact the reason why you get omega. If you did not have static friction, you would only get V, right? It would slide down, but it wouldn't rotate. It'd be like a block. It'd be no different. But here you get omega because of static friction. Static friction, makes sure by pointing upward that this thing rotates like this. So as long as we account for omega in our conservation of energy, we've accounted for friction and we are allowed to write conservation of energy. So this is really important because we've hammered so hard that if there's friction, conservation of energy is out. Yes, but not in the case of rolling without slipping. Because I need friction for rolling without slipping. Okay, cool. The only caveat is that, well, because it's rolling without slipping, I have to account for omega. In accounting for omega, I account for friction. Okay? So let's write conservation of mechanical energy applied to this thing. Now, we are going to apply conservation of energy to this thing by tracking its center of mass. Okay, so what's the kinetic energy at first? Well, it ought to be, if we're rolling without slipping, 1/2 mv0 squared plus 1/2 I center of mass omega squared. We'll call it omega 0 squared maybe. But because we're at rest, this is 0 and this is 0. So there's no kinetic energy at the beginning. And then we have mgh potential energy at the beginning, is equal to at the bottom, okay, now we do have kinetic energy. We have 1/2 m v center of mass squared, and I have to add the rotational kinetic energy because when I have rolling without slipping, I need both of these guys. Okay, now be very careful. A lot of you are going to want to write 0, force of habit, but we track the height of the center of mass. The center of mass is not on the ground. It sits a height r above the ground, therefore it has potential energy mgr. Okay, so this is really important to keep in mind, that when you apply this conservation of energy equation, when you look at potential energy, you follow the center of mass. Why? Because the center of mass is where the weight force is applied. And the weight force mg is what creates mgh, right? Is what is associated with mgh. So I need to track the height of the center of mass, which is not 0, at the bottom of the incline. Okay, but if I do that, then fair enough. I'm going to get something pretty straightforward. I'm going to get mg h minus r, if I subtract mgr on both sides, is 1/2 m v center of mass squared plus 1/2. Now I center of mass is given. It's 2/5 m r squared omega squared. I want to find v center of mass. The problem is I have one equation and two unknowns because I don't know v center of mass and I don't know omega. But recall that rolling without slipping allows me to write that v center of mass is equal to r omega. Okay, so then turns out this term right here, which is r squared omega squared, is actually equal to v center of mass squared. Okay, so I get mg h minus r is equal to 1/2 of mv center of mass squared plus 1/5 of mv center of mass squared. That's going to be 5 plus 2 is 7 over 10 mv center of mass squared. Okay, so mass cancels out, and I get v center of mass is equal to the square root of 10 g h minus r over 7, which is an extremely classic question, right? To have something rolling without slipping down an incline, something like that. It doesn't have to be a sphere. It could be a cylinder, a hollow sphere, whatever, a hoop. The difference is going to be an I center of mass, right? But the approach is going to be the same in both cases. And you're going to write conservation of energy. Just make sure that you remember that the height of the center of mass with respect to your reference is what matters when it comes to gravitational potential energy. All right, so this should wrap up the torque chapter. We've talked about equilibrium, torque net equals I alpha in kinematics, and then today rolling without slipping and conservation of energy. The only fringe topic left is angular momentum, and we can revisit that for the final. But for now, we should be on track when it comes to midterm 2 and all the things surrounding torque that you might be asked to know and to solve for. So again, I know I've said this many times, I chose to go through the torque chapters in a certain order, which I think just build gradually on each other, and it makes it a little bit clearer the different parts of these chapters, and just again, let's just progress logically through them. Likely it is not the order in which it was done in lecture. That's for reasons that escape me. I don't know why you would do a different order than this one, but fair enough. So, you know, if you're reviewing, you might want to watch the 3 live streams in sequence, because like that you can sweep through the whole content and you can tie it out with what you did in lecture. But at least what we did together is, you know, it builds on itself, and slowly but surely we introduce new things. We start with torque, and then we add moment of inertia, and then we add kinematics, and then we add rolling without slipping. So anyway, that was my decision to do it that way. So this wraps up torque. It also kind of wraps up all of mechanics to this point. Like everything we've done from day 1 to today is one big consistent, coherent whole. After this, it's going to look very different. Fluids are extremely different, oscillations and waves and whatever, and it's really going to be kind of self-contained chapters that don't have much to do with this, although there's some things that would be reminiscent of all of mechanics. But say that to say this, that we've done kind of the bulk of the course. And now there's still stuff to cover, of course. It's not like we're done, but the last third looks different from the first 2/3 of the course in that sense, that all the chapters are kind of independent from each other. And they're not necessarily bad. There's a few nice ones, like thermo and fluids are super easy, so which is nice because it means we only have to worry about oscillations, which is probably the worst, and waves, which once you get waves, waves are so straightforward because we don't do them in depth that it's okay. You just got to figure out what's going on and understand really what you're looking at, but there's no complicated math involved in those. So anyway, best of luck for midterm 2. It's getting close. Hope things are going well. I know that it gets really crazy after midterm 1, so hopefully you have time to sit down and do some of this and not have 3 exams the same day, which seems to happen more often than not. But best of luck. Next week we will move on to fluids, and we'll continue from there, and we should be wrapped up by end of November, so that it's just from there on out it'll be review for physics. So as always, thanks for watching, and feel free to reach out if you need help or if there's something that I said that didn't make sense. Always happy to clarify. Take care.